Good morning, everyone. My name is Pencil. I come from TU in Munich. Today, I want to talk about our work, which is about the cross-platform malware detection. We use the representation learning on graph to extract features from the raw executable file. The name of our work is HawkEye. This work is cooperated with Yui Zhang. He's from the Tongji University of China, and also Claudia Eckert. She is my supervisor in TU Munich, and also the opposite list, he's from the Delft University of Technology. The agenda of our presentation includes introduction. In this part, we will talk about our motivation and also our contribution, of course. And then second section, we talk about the related work. Here we will talk about the different directions in the malware detection field and also the advantage and the disadvantage. Of course, we also include the difference between our work and also the related works. The second section, the second part, we will talk about the system design and also implementation. Here, we will give an architecture about our work and also some detailed information about each modules in our architecture. The fourth part, we will talk about the evaluation. Here, we will talk about the setup of our experiment, how did we collect our data set, and also, of course, some result compared to another related works. Last but not least, we also give our conclusion in the last section. Currently, with the development of the mobile device and also device, more and more device equipment are touched by the malicious programs. So therefore, we need many types of the malware detection system in different level. Here, actually, in the malware detection field, there are many challenges for our security researchers. One primary challenge is, we need one common malware detection system for different types of the device and different types of the platform. The other challenge is the obfuscation technology. Currently, more and more malware authors are using obfuscation technology, which could be negatively influence the existing malware detection system. So, for example, if we use some malware detection system which is based on the sequence of the instruction on API, if we use the string encryption, which is the type of the obfuscation technology, if we use a string encryption, so the string, the sequence of the API could be influenced. So that means we cannot use the API call information to detect the malware behavior. Here we show some example, how we use the cross-platform in our application and also the RCT environment. However, no matter which type of the platform, the operating system we used on which type of the architecture, we can get the control flow graph as the structure information from the program. So that means that if we want to solve the cross-platform multi-text system, control flow graph best way is the right direction. So the contribution of work includes, the first one is we design and implemented a HawkEye, that is the cross-platform malware detection system. We use the control flow graph and the graph neural network to do the graph embedding thing, which is also use the techniques from the NLP fields. The structure of our work includes three primary modules. The first one is the graph generates. The second one is the graph neural network-based graph embedding, and the third one is the machine learning-based classification. The result of our work outperformance numbers malware detection solutions. For the related work in the malware detection history, we use the feature code, which is a unique code for each malware samples. But the disadvantage is for the no-seen malware. malware, we cannot get the feature code in advance. So that means we cannot detect and see malwares with this type of the methodology. With the development of the machine learning and deep learning, we also consider use of this machine learning deep learning in the malware detection. The first methodology is the use like the malicious API call and from the config file on the manifest file to do the malware detection. For the Android application-based malware detection, we also use the performance-based methodology. Of course, network traffic is also a type of the feature to use to detect malicious behavior. Last but not least, we also get features from the program code itself. That means we can extract from control flow graph, API call, function call graph from the program code itself. Except the CFG and the config API call, we also can get another type of the patterns, such as the convert the executable file to the image, and we do the malware detection, like the image classification. In table 1, we list the difference between our work and another exciting work. For example, for the only use the CFG, we can get the Jimmy, Adagio, and another works. If we consider the byte sequence, we have the Ember, malcover, and also if we want to do the cross-platform work, we can find another work like this one, which use a call graph and a graph embedding. But that is not for the cross-platform. Our work, HawkEye, we target to the cross-platform. We use the repeated learning on graph. The architecture of our work is shown in figure 1. We input the executable binary and get the benign or malicious result. The architecture of work is here, which includes the control flow graph extracting, graph generated, and also the graph embedding based feature preparing and graph embedding here. The mathematical module behind our system architecture is here. We input the graph and use the labeled value and get our loss function. Here, the purpose is predict whether an executable file is malicious and benign. Use our system. We separate our architecture into 3 modules. The first one is the graph generated, and the second one is the feature embedding, and the last one is MLP-based classifying. For the graph generated, that means that we extract a follow graph from executable binary. Here, in our case, we extract the static and the dynamic control flow graph, and also the function call graph. All of them have the same representation. That is a graph, and we have the node and the edge. In our case, the node is a function on basic block. The edge could be call and call on jump, return some the control flow instruction. The dynamic control flow graph and the function call graph, in our case, are reduced graph of the static control flow graph. For the feature embedding, we also have the 3 submodules. The first one is the mnemonic embedding. What is the mnemonic? Actually, that is the opcode in the machine instruction, like the move, add, and the sub. For the operator, we also have the immediate number, register, and also memory. But in our case, we didn't only consider the mnemonic, which will lost operator information. But operators have their inherent variability. That means that we have the OOV problem. And in our case, operator is not very important compared to the behavior, which is stand for by the mnemonic opcode. So here we use the opcode embedding, and we use the escape grammar sampling for the sampling based to vector for our opcode embedding. After we get the opcode embedding, we also do the basic block embedding, which is used for convert the control flow graph to the target control flow graph. We use a very simple nominalization based on the maximal and the minimal value. We picked the first element of the vector is the maximal and the maximal and minimal value. After we get the black embedding, we will do our graph embedding, which is based on the struct2 vector. And in our case, we use the function on basic block to as our node, and also call jump returns some control flow instruction is also as an edge. After we convert the graph to the vector, we use the MLP-based classification system to do the malware detection. Our MLP network include one import and two hidden layer with the 32 unit and also the one output. We use the hidden loss as our loss function during the training. For the experiment setup, we use the TensorFlow as our machine learning framework, and also Angola, which is used to extract graph from the binary. We also use another library like the NumPy, Skyline, and so on. We collect our data set by ON from the VirusTotal and the Androzome. Actually, in total, we didn't get too much malware samples for the Linux system. We get enough for the Windows and Android OS. We split our dataset with 16 for training, 20 for validation, and 20 for the testing. In order to use the word2 vector, which is the natural language processing technology, we should have the power law distribution for the word. What it means the OP code in our case. Also, our result is shown like that for the no matter for the Intel architecture ARM or Android Dalvik virtual machine, all of the instruction follow the power law distribution. Our malware detection performance is also very nice, especially for the Android application malware detection. Compared to Adagio, we get better accuracy, precision, recall, and the F1 function. For the Windows malware detection, actually, we didn't get a very high accuracy and precision, but compared to related work, we get the recall, good recall, and better recall and F1. In total, our system is most standable compared to other related works. We also evaluate the virus hyperparameters, how virus hyperparameters influence our system. We test for the different epochs during training and also the different learning rates, different embedding size. All of them get very nice results, but we can see that for the when we use 0.005 learning rate, we get the best accuracy with here, and also the embedding size have a minimal influence for the final result. Yeah, go back to return back to recall back our second motivation. We also evaluate our framework and the influence of obfuscation, obfuscated samples. Here, our framework also works very good compared to ProGuard and the Durambi for different classification. Yeah. We also from the figure 5, we also see how the different obfuscation technology influence our framework. We can see here, especially for class encryption and the string encryption, we get very standable result. That's all. Let us conclude our work. We design and implement HawkEye. That is a cross-platform malware detection system. We use control flow graph and the graph neural network to do our graph embedding. Our system includes 3 primary modules. The first one is the graph generate, and the other one is the graph embedding. The last one is the malware machine learning based classification. Our result outperforms numbers malware detection solution. Okay, thanks. Welcome to any type of the question and the comments.